Hello, this is Ali Reza. I'm the third ESR in the WaveComBE project. I'm going to talk about my research results in last 3 years of the program, and it will be about design and implementation of 28 GHz phased arrays based on gap waveguide. An array of antenna based on gap waveguide has been designed in this work. This array is working from 26.5 up to 29.5 GHz, which makes it suitable for 5G applications. This antenna has 8 elements in the horizontal axis, and each element has 8 slots in the vertical axis. This antenna has 2 layers. First is the top one is radiation layer, and the bottom one is distribution layer. Distribution layer consists of ridges and pins to feed the slots on the slot layer. This antenna has active spirometer less than -10 dB in the whole frequency band and the all scanning angles. In this slide, you can see the active radiation pattern of the antenna in E-plane at 2 frequencies. The antenna shows the gain of on average 23 dBi at broadside angle, and side lobe level remains below -10 dB in all scanning angles. The next antenna is a dual polarized antenna based on gap waveguide. This antenna has its orthogonal polarizations in ±45 degree angles. This antenna covers the frequency band of 24.25 up to 27.25 GHz, which makes it again suitable for 5G applications. You can see that at the bottom of the slide the radiation pattern of 2 polarizations in copolar and crosspolar. The next work is about the transitions from microstrip to gap waveguide technology. We have designed 3 contactless vertical transitions for 28 GHz steerable array antennas. The array antennas at 28 GHz need to have a good integration with PCB technology. So we have designed 3 types of transition can perform quite well in this frequency. You can see the performance of these 3 transitions at the bottom of this slide. We have integrated these transitions with an actual phase antenna array based on gap waveguide, and you can see the results of the reflection coefficient at the bottom of the page. The next work is about design and fabrication of a high ERIP phased array antenna using gallium nitride technology. It is known that there is a high path loss in millimeter wave frequency, which drives the need for high ERIP base stations or access points. It is estimated that about 45 to 60 dBm ERIP is needed for base stations at 28 GHz frequency. And gallium nitride is recognized as a good candidate for power amplifier for such an applications. Also, it is good option for wide bandwidth requirements in 5G. Because of very high power density of gallium nitride, we need to consider the cooling capability of the whole phase array. Gap waveguide technology as a whole metallic structure offers a good thermal handling, which is needed for gallium nitride PA. In this work, we have designed a 50 dBm ERIP at 9 dB backup from saturation point, and it can dissipate heat in 2 direction of the PCB. The radiation pattern properties of this antenna is very similar to the first antenna presented. The next work is about 16 by 16 elements, 45 degree slant polarized phased array antenna. For large phased arrays at 28 GHz, there is a disadvantage of complex PCB design. This complexity of the PCB design usually associates with high cost and low yield rate. For example, you can see that a 7-layer PCB ends up with a narrow bandwidth of only its antenna element. Then it limits the performance of its RFICs. To achieve a high bandwidth antenna element, the number of layers of the PCB should be increased. For example, at this work, we have 2 GHz of bandwidth. And recently, with a 12-layer PCB, a good bandwidth of 4 GHz has been achieved. For this problem, we have designed a gap waveguide-based phased array, which it only uses 6 layers of PCB. It has a low loss, both ohmic and mismatch, of about less than 0.5 dB. It covers 26.5 up to 29.5 gigahertz, and it also covers a wide scanning range of plus 60 to minus 60 degree in azimuth and plus 10 to minus 10 degree in elevation. The antenna has been fabricated and characterized completely. You can see as an example the radiation pattern of the copolar and cross-polar of the antenna in broadside and azimuth minus 40 degree scanning angle compared with simulation. Thank you for your attention. For more information about my research and publications, you can look at my page at wavecombe.eu.